Hi everyone, it's Nick. I'd like to say hello and thank you for choosing to participate in this study. It helps me out, and I also hope that you find this information valuable and consider applying it to your current practice. The title is The Environmental Effects of Anesthetic Gases. This is just a quick overview of what we'll be covering today. Um, some basic atmospheric sciences, the environmental effects of anesthetic gases, how we can reduce our impact, and also some economic benefits. So I'd like to try and stress the significance of this topic with a few facts here. All of the anesthetic gases that we're familiar with and use are potent greenhouse gases. They're hundreds to thousands of times worse for the environment than carbon dioxide. Isoflurane and nitrous oxide in particular have profound ozone depleting potential. The use of fluorinated gases and their emissions have increased 69.7% from the years 1990 to 2017. The rate of hydrofluorocarbon emissions has increased 239.9% in that same time period. The rate of surgeries, as we know, continues to rise every year, and anesthetic gases are deemed medically necessary. So there are no policies or regulations that control their discharge into the atmosphere at this time. Now we'll move on to basic atmospheric science. I'd like to preface this all with how the topic kind of came to be. So, as you know, chlorofluorocarbons, typically know them as CFCs. So CFCs and other ozone depleting substances were used in many industries and products. And that was kind of up until 1985, they discovered the ozone hole over Antarctica. And so, they started to develop some legislation. And in 1987, they developed the Montreal Protocol of 1987. The Montreal Protocol was aimed at banning these ozone depleting substances. However, there was, a little fine print that says anesthetic gases are medically necessary, and rightfully so, but they were left out of the protocol. So there were no policies or no regulations regarding their discharge into the atmosphere, and they were kind of, not included in this Montreal Protocol. And so with the ban of CFCs, it led to the increased development and use of HFCs. HFCs are very similar to CFCs, and we'll touch on that a little bit more later. One thing I've noticed is that people tend to clump the ozone layer and greenhouse gases into the same thing. And while they are on the same subject, they're very different, and I'd like to address that. The ozone layer is essentially made up of ozone, and it's found in the stratosphere. Now, ozone is a molecule made up of 3 oxygen atoms. And the ozone layer is important because it absorbs radiation from the sun, most importantly, UVB rays. And the significance of the destruction or depletion of the ozone layer is that more harmful UVB radiation is going to reach the Earth's surface. This is associated with cancer, cataracts, disruption of ecosystems, and biological cycles. So to the right, you can see that we have the chemical structures of most of the anesthetic gases that we're familiar with. And if you look, halothane has a bromine atom on it, isoflurane and enflurane have chlorine atoms. And so I briefly said it earlier, but nitrous oxide and isoflurane have ozone depleting properties, as well as halothane and enflurane, but I didn't cover them in this lecture because we don't typically see them in practice. Now, one chlorine atom, for example, can destroy 100,000 ozone molecules before being eliminated from the stratosphere. Greenhouse gases are gases that are in the atmosphere that absorb and reflect back infrared radiation that would otherwise escape into space. Now, there's many different types of gases, but essentially the potency of each gas and their greenhouse gas effect is determined by their atmospheric lifetime, how much infrared radiation is absorbed during its lifetime, and whether there are naturally occurring species that absorb the same wavelengths of that gas. And so The significance of greenhouse gas emissions are climate change, weather extremes, disruption of ecosystems and biological cycles, as well as rising sea levels. So to sum it up, you have the ozone, which absorbs radiation and protects the Earth, and then you have greenhouse gases, which accumulate in the atmosphere, and they trap and reflect back infrared radiation that would normally escape into space. With that information under our belts, now we can move forward and talk about the environmental effects of these anesthetic gases that we use every day. For a brief summary of the anesthetic gases, all of our volatile anesthetics are fluorocarbons and greenhouse gases. Now we learned that isoflurane is a chlorofluorocarbon, or a CFC, meaning that it's a substance that contains carbon, fluorine, and chlorine. Now, sevoflurane and desflurane are hydrofluorocarbons, meaning that they're a substance containing hydrogen, fluorine, and carbon. Now, with the Montreal Protocol, they started to reduce and eliminate the use of CFCs, which brought on the development and increased use of HFCs. And then we also have nitrous oxide, which you're familiar with, is 2 nitrogen atoms and an oxygen atom. Nitrous oxide is not a fluorocarbon, but it does have ozone depleting properties. All of these gases are minimally metabolized and exhaled unchanged into the atmosphere. This is a very brief chart and just another way to look at this. Each one of these gases does have greenhouse gas properties. It is going to trap and reflect radiation that would otherwise leave the Earth's surface. Isoflurane and nitrous oxide, as well as enflurane and halothane, but for these 4 gases, they have ozone depleting properties. Sevoflurane and desflurane, HFCs don't really have that ozone depleting property in them. The global warming potential is a very important scale. It's used to measure the potency of greenhouse gases. In other words, it's going to take into account the heat trapping efficiency and the lifespan of atmospheric gases. So let's put that into perspective. The GWP is usually measured over 20 years or 100 years. And the GWP 100 is going to compare the energy absorbed by 1 ton of a greenhouse gas relative to the energy absorbed by 1 ton of CO2 over a 100-year period, with a higher absorbance indicating a worse effect. Now, the GWP20 is going to compare the energy absorbed by 1 ton of a greenhouse gas relative to the energy absorbed by 1 ton of CO2 over a 20-year period. And so carbon dioxide is going to serve as the reference point with a GWP of 1. It's a GWP of 1 at 20 years and a GWP of 1 at 100 years. So I forgot to mention in the last slide, but I did put it in asterisks, I hope you saw. Any gas that has an atmospheric lifespan of greater than 2 years is expected to reach the stratosphere in significant quantities. And that's important because all of these gases do have different atmospheric lifetimes. So we'll talk about isoflurane first. We already know that it's a CFC. It's a chlorine-containing fluorocarbon that has ozone-depleting properties and greenhouse gas effects. So at the bottom, you can see the lifetime, atmospheric lifetime, is 3.6 years. So the GWP of 20 over 20 years is equal to 1,401, and the GWP 100 is 510. So this makes sense, and I'll kind of spell it out here. 1 ton of isoflurane, even though it has a short atmospheric lifetime, is very potent in the beginning. Okay, so 1 ton of isoflurane has the same effect as 1,401 tons of carbon dioxide over the course of 20 years. So the GWP 100, 1 ton of isoflurane, has the same effect as 510 tons of carbon dioxide over 100 years. Sevoflurane is the next gas we'll talk about. And we know that sevoflurane is an HFC, no longer has the chlorine atom in it. It is a hydrofluorocarbon. So sevoflurane does not have ozone depleting properties, which is great, but it is still a potent greenhouse gas. The atmospheric lifespan of sevoflurane is 1.2 years, and that is the shortest out of all the anesthetic gases. So to spell these out again, 1 ton of sevoflurane has the same effect as 349 tons of carbon dioxide over the course of 20 years. And 1 ton of sevoflurane has the same effect as 130 tons of carbon dioxide over 100 years. Desflurane is the next gas we'll talk about, and we know that desflurane is an HFC, so it lacks the ozone depleting properties, which is good. However, desflurane is the most potent greenhouse gas out of all the gases that we use. And you can see here that the GWP of 20 is 3,714, and the GWP 100 is 2,540, with an atmospheric lifetime of 10 years. So very, very potent, even though it doesn't stay around too long. But 1 ton of desflurane is equal to 3,714 tons of carbon dioxide over the course of 20 years. And 1 ton of desflurane has the same effect as 2,540 tons of carbon dioxide over the course of 100 years. Nitrous oxide is a little bit different than the fluorinated gases because it's a molecule consisting of 2 nitrogen atoms and 1 oxygen atom. However, nitrous oxide does have both ozone depleting properties and greenhouse gas effects. So what happens is nitrous oxide reaches the stratosphere, has a very long atmospheric lifetime of 114 years, and it's broken down into nitric oxide as well as nitrogen dioxide. And those two compounds essentially interact with the ozone and destroy it that way. We can see here that it also has a global warming potential over 20 years of 289 and a GWP 100 of 298. To put that into comparison, 1 ton of nitrous oxide is equal to 289 tons of carbon dioxide over 20 years and 298 tons of carbon dioxide over 100 years. I think it's important again to highlight this atmospheric lifetime of 114 years. It stays up there for a very, very, very long time. Here we have a quick chart summary of the 4 gases that we're talking about in detail. We can see that the lowest greenhouse gas effects come from nitrous oxide in both the 20-year and 100-year category. That may be a little bit deceiving though, because nitrous oxide is used a little bit differently than our volatile anesthetics. As you know, it comes from the pipeline and it is essentially emitted continuously. And we also have the highest in those 2 categories as desflurane. We have the atmospheric lifespan on the right side, the lowest being sevoflurane with the longest being nitrous oxide. So there's a lot of things that come into play, and we'll discuss these more later. But as you can imagine, the worst possible combination would be nitrous oxide as a carrier gas for desflurane. It's kind of double whammy there. So let's put that all into perspective, because that was just a bunch of numbers I threw at you. And so let's take a look at the most common flow rates: 2 liters per minute for sevoflurane, 1 liter per minute for iso, as well as desflurane. So on a per Mach hour basis, the total life cycle greenhouse gas impact of desflurane is more than 20 times higher than that of sevoflurane or isoflurane. Nitrous oxide, as you know, is a little bit different. It is a fresh gas and has low potency, requires high concentrations, and has a very long atmospheric lifetime. And so the greenhouse gas effect of nitrous oxide is actually similar to that of desflurane. So we mentioned this on the last slide. When you use nitrous oxide as a carrier gas for any of the volatile anesthetics, the greenhouse gas impact profile is significantly worse. I think bringing things into perspective is very important. It puts it in kind of a familiar profile that is easier to understand. So this article here by Hannah and Bryson in 2019, they sought to, translate these emissions into distances that we drive in a car. And they used 1 liter per minute total fresh gas flows for each of the gases. So I know that's a little bit different for sevoflurane. Usually you see people running it at 2 liters per minute. But so 1 hour at 1 Mac of Sevo was 6.5 kilometers. 1 hour at 1 Mac of isoflurane was equal to 14 kilometers. 1 hour of 60% nitrous is equal to driving 95 kilometers, while 1 hour of 6% desflurane is equal to driving 320 kilometers. So this is where you can see where if you add nitrous as the carrier gas, you're going to increase the environmental impact. This is another really great study that I found by Alexander and colleagues from 2018. And what they did was they wrote about 7 British Columbia hospitals that over 4 years reduced their use of desflurane and increased their use of sevoflurane. And then they calculated the difference in CO2 equivalents. So over those 4 years, they were able to reduce their carbon equivalent emissions by 8,900,000 kilograms, which totaled 66% reduction. And again, to put this into perspective to something that we can quantify a little bit easier, this is equivalent to 1,700 personal vehicles driving 13,760 miles each per year. And so if you look at this chart to the right, you can see that the dotted yellow line that's increasing, that is the liters of sevoflurane that they used, while you have the black dotted line, and that is the liters of desflurane that they used over those 4 years. And the graph there, you can see those are the carbon dioxide equivalent emissions in the red. And so, I mean, that's great. They were able to essentially just reduce their emissions by using more Sevo and using less desflurane. Here are some more statistics about the environmental effects of anesthetic gases. In 2006 alone, it was estimated that 35,000 tons of nitrous oxide were used for 70 million procedures in the US alone. And so I did the math here for you guys, and that's equal to 10,430,000 tons of carbon dioxide. Down here, you can see that using desflurane for 1 hour is equivalent to 235 to 470 miles of driving using 1 liter and 2 liter per minute fresh gas flows respectively. So I kind of split the difference there, and I did, let's say, 1.5 liters per minute fresh gas flow. So if you used 7 hours of desflurane at 1.5 liters per minute, that would be equivalent to driving 2,468 miles. And that's essentially a one-way trip to San Diego over your workday. So let's talk about how we can reduce impact. A couple things. We can utilize low-flow anesthesia. We can avoid nitrous as a carrier gas and only use desflurane when clinically necessary. Low-flow anesthesia is great. It's not something that I've seen very much, but I've done a lot of research on it, and there's some really great stuff. I'm excited to share this with you. So minimal flow anesthesia would be defined as 0.5 liters per minute. And then you have low flow anesthesia, which is generally defined as 1 liter per minute. So up to 80 to 90% of the environmental impact of anesthetic gases could be reduced with closed circuit anesthesia. However, that's not, totally possible, but to a lesser degree, we can accomplish those results with low flow anesthesia, which is much more realistic and achievable. So lowering the flows reduces, the amount of volatile anesthetic that is going to leak out of the breathing circuit through the APL valve into the scavenging system and out the top of the hospital into the atmosphere. Low flow anesthesia is great. It presents many benefits, and these include less atmospheric and operating room pollution. There are also significant economic savings associated with low flow anesthesia, and it humidifies and warms the breathing gases that your patient gets. Some drawbacks include you may desiccate the carbon dioxide absorbent faster, and you will have slower changes in alveolar concentrations. So this is something I just want to touch on briefly, and I have more information and resources that I can send you if you're interested in this topic. There's actually a very extensive manual that Draeger put out for implementing low flow, minimal flow, and metabolic flow anesthesia with their machines. So minimal flow we know is 0.5 liters per minute, and provided the system is completely leakage free, you can actually reduce your fresh gas flow until you're matching the gas volume with which the patient is absorbing and metabolizing while under anesthesia. So typically you would see, an oxygen consumption of 3.5 milliliters per kilogram per minute. And so if you had a 100 kilogram patient, you could run your flows at 0.35 liters per minute. So these two things I would not recommend with sevoflurane just because of the FDA regulations. And we'll talk about that a little bit more as well in the coming slides. Compound A is a very big thing that people bring up when I discuss low flow anesthesia with them. And so it is very real. Sevoflurane breakdown in CO2 absorbents does produce compound A, but that's not true for all CO2 absorbents. It's only in those CO2 absorbents that have strong bases, such as sodium hydroxide or potassium hydroxide. So I think it's important that you be aware of what type of CO2 absorbents your facility is using, because CO2 absorbents like Amsorb and litholine do not produce compound A. An interesting fact here in the Miller's anesthesia textbook, fresh gas flows of 1 liter per minute results in maximal concentrations of 20 parts per million in soda lime and 30 parts per million in berylime. With these next few slides, I'd like to just bring this topic to light and present you with some studies and some information that I found. And so we've all heard of the study where compound A was found to be nephrotoxic in laboratory rats. And to sum that study up, there was mild injury at 50 parts per million times 3 hours, totaling 150 parts per million exposure to compound A. There was moderate to reversible injury in rats at 200 parts per million, and the lethal dose in 50% of rats was 1,000 parts per million. However, there have been numerous studies that show that compound A is not nephrotoxic in humans. Multiple studies with exposures to levels greater than 200 parts per million showed no changes in renal lab values. So with these rats, they have this beta lyase activity, and essentially that is what's responsible for causing the kidney injury. However, human kidneys have far less beta lyase activity. So here we have a couple older studies back when sevoflurane was a new drug. And so we can see here by Beadle and colleagues in 1997, they studied the effects of low-flow sevoflurane anesthesia on renal function. And what they did was they compared low-flow sevoflurane, high-flow sevoflurane, and low-flow isoflurane. And during the study, they found no evidence of renal injury in humans. We also have Konzen and colleagues from 2002 who studied low-flow isoflurane versus sevoflurane in stable renal insufficient patients, and they found no significant differences in renal lab values after using low-flow iso and low-flow sevo. So here we have a chart on the accumulation of compound A at different fresh gas flow rates in the system. And this is taken right from the FDA website on sevoflurane. Definitely encourage you to check it out. It's very interesting. And so you can see here the different levels of compound A. Say at 1 liter per minute, it's about 15 parts per million. At 2 liters, it's 10 parts per million. And we'll cover this a little bit more in the next slide as well. This is another very important graph that I'd like to share with you all, and it was taken from the exact same document on the FDA website on sevoflurane. And what it's showing is the accumulation and exposure to compound A when using sevoflurane at 1 liter per minute fresh gas flows. So you can see that at 1 liter per minute and 2 hours of anesthesia time, you're getting upwards of 40 parts per million of compound A. And then at around 4 hours, you would reach approximately 100 parts per million. And I just like to bring these things to your attention so that you can see the data for yourself and think about it that way. This text box up here is also right from that same document on the FDA, and it's talking about compound A exposure and how much fresh gas flow you should utilize. And so I know I've been talking about all these different studies saying that the accumulation of compound A is not significant and that it's safe in renal insufficient patients, but I'm not here to ask you to break the rules or to ask you to do something that might get you in trouble with litigation. I'm here to ask you to follow the guidelines. It's very important. This is very important. So what the FDA states is that you can use sevoflurane at 1 liter per minute for up to 2 MAC hours, and then you should increase your fresh gas flows to 2 liters per minute. And so this is important because, not all of our surgeries, I wouldn't even say the majority, are over 2 hours. So you would be able to use low flow anesthesia, sevoflurane at 1 liter per minute for up to 2 MAC hours, and then you can adjust your fresh gas flows if it goes above 2 MAC hours to 2 liters per minute. This way, you're following the guidelines and you're reaping the benefits of low flow anesthesia. The next topic we'll talk about very briefly is the economic benefits of low flow anesthesia. We all know healthcare is very, very expensive, and cost is something that we should all be conscious of. And so I found these 3 articles here, and I'm just going to kind of summarize them very briefly. But you can see that there's some very, very big benefits to running low flow anesthesia. So in a study by Kennedy and colleagues, it was estimated that they could save $200,000 a year by reducing their maintenance fresh gas flow rates by 1 liter per minute. This was in a hospital that performs 20,000 surgeries each year. And so I'm not sure how many surgeries you guys are doing between all of your sites, but that's food for thought. That's a lot of money. Carter and colleagues they saw a 25% decrease in volatile agent expenses by promoting low flow anesthesia over 1 year. And then this one here, this is a lot of money. This is, $365,000 a year, equaling $1,000 per day. But Miller and colleagues saw the biggest savings by utilizing isoflurane, which is the cheapest anesthetic, and isoflurane. So, utilizing the cheapest anesthetic and low flow anesthesia, they were able to save a lot of money. And so, this may be something that, you guys could implement and save some money as well. Just some closing remarks. I want to say thank you. It really means a lot that you took the time out of your busy schedules to participate in this research project for me. I really hope that you learned some valuable information today, and I hope that you consider implementing it into your practice. As far as the follow-up post-survey, please don't forget to do that. It's very important. Essentially, I'm going to be comparing data from the pre-survey to the post-survey. So without the post-survey data, I can't do that. The link can be found in the description below. And once again, thank you and enjoy the rest of your day.